Welcome to Calm and Clever. It's lovely to have you here tonight. Wherever you are right now, settle in. Maybe you're under a blanket with the lamp still on, or maybe the room's already dark and the screen is the only light left. Maybe you're on a train or a couch, or that particular corner of the bed you've claimed as yours. It doesn't matter where. What matters is that you've found a quiet pocket of the night, and you've decided to spend a little of it here with me, drifting through something strange and beautiful. So before we begin, let me just say, I'm glad you came. And where in the world are you watching from tonight? I always wonder. Some of you are deep in the small hours, the kind of dark where the whole house has gone still. Some of you are just getting started, the evening's still warm around you. Wherever you are, whatever time it is, in your corner of the world, you're welcome here. If you enjoy these slow journeys and want more of them, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me genuinely rely on it, and I don't take it for granted. And to those of you already subscribed, who come back night after night, thank you. Truly. You're the reason I keep making these. Now here's my one small promise to you. I'll try not to make tonight so interesting it keeps you awake, but if it does, well, at least you'll have learned something lovely in the trying. A fair trade, I think. And honestly, there's no need to follow every word. None at all. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here. The star will still be turning. You can let the words wash over you like water and let your mind go soft and loose, and you'll lose nothing by sleeping. That's rather the point. So, let's begin, shall we? Slowly, softly, one small mystery at a time. Tonight, I want to tell you about something most people think they already understand. You've probably heard the line before. It gets repeated everywhere, in every documentary, in every breathless little video about the cosmos. The line goes something like this. Somewhere out there are stars so dense that a single sugar cube of their material, just one small white cube, the kind you'd drop into a cup of tea, would weigh about 1 billion tons. 1 billion tons in something the size of your thumbnail. And it's a good line, it really is. It stops people in their tracks. It's strange enough to be remembered and just believable enough to be true. But here's the thing I want to tell you tonight, the thing that almost nobody bothers to say after they've delivered that sentence and moved on. That famous line, the billion-ton sugar cube, is the least interesting thing about these stars. It's the part everyone stops at, and it's only half true. Let me explain what I mean by that gently, because it's lovely once you see it. When people say a sugar cube of this stuff weighs 1 billion tons, they're talking about the very heart of the star, the deep, crushed center where the matter is squeezed harder than anywhere else. And down there, yes, the numbers are staggering. The average density of one of these stars runs somewhere between about 370 quadrillion and nearly 600 quadrillion kilograms per cubic meter. I know those words are slippery, so let me give you something to hold on to. Imagine the densest stuff you've ever touched, a lump of lead, say, or a bar of gold, heavy enough that you have to brace your wrist to lift it. Now imagine something so much heavier than that, so much more tightly packed, that the comparison stops making any sense. That's the heart of this star. To put it another way, the matter inside an ordinary atom's nucleus, the absolute densest stuff in your own body, packs to about 230 quadrillion kilograms per cubic meter. And the core of this star is denser even than that. It is, in a real sense, like one enormous atomic nucleus, the size of a city, holding itself together against gravity. So the famous line isn't wrong. Near the core, a sugar cube really would weigh something close to 1 billion tons. But, and here's the half that gets left out, the star is not the same all the way through, not even close. If you could fall into it slowly, layer by layer, the density wouldn't be one fixed number. It would rise as you fell. The outer skin of the star, the crust, is far, far lighter than the core. And as you sank inward, the weight of that single imaginary sugar cube wouldn't just creep up, it would multiply. By millions. The crust might give you a sugar cube heavy as a mountain, which is astonishing enough. But fall deeper, and that same little cube grows to the weight of a small moon, and deeper still, and it becomes that famous billion tons, and at the very center, it would be heavier than anything that single repeated sentence has ever bothered to tell you. So the boring version of this story stops at the sugar cube and calls it a day. We're not going to do that tonight. Tonight we're going to finish the sentence, because here's what's actually new and what almost nobody talks about. We didn't just calculate these stars on a chalkboard. We didn't just guess. We finally genuinely measured one. We measured how big it actually is. We measured the shape of the hot patches glowing on its surface. We found a hard ceiling, a precise weight above which no such star is even allowed to exist. And we mapped the strange layered world inside it all the way down to the one place where modern physics simply holds up its hands and admits it doesn't yet know what's there. That's our journey for tonight, from the famous half-truth all the way to the honest unknown at the center. And we'll take it slow. There's no rush. There's never any rush here. But before we can talk about how we measured one of these things, and the measurement really is the heart of tonight, the part that makes we finally know feel earned instead of just asserted, we have to talk about where these stars come from in the first place. And to do that properly, we have to go back, way back, to a time before anyone had ever seen one, when they existed only as an idea in two stubborn minds. Let me set the scene for you. Picture the world as it stood in the early 1930s. The atom was still a fairly fresh idea, and physicists were busy taking it apart, finding the pieces inside it. For a long time, they'd known about two of those pieces. The proton, with its positive charge, and the tiny electron, whirling around the outside. But there was a gap in the picture, a missing piece. The arithmetic of the atom didn't quite add up. There seemed to be extra weight in the core that the protons alone couldn't account for. Something was hiding in there. Something with no charge at all, which is precisely what makes it so hard to find. A particle that's electrically invisible slips right past most of your detectors like a ghost through a wall. And then in 1932, an English physicist named James Chadwick finally caught it. The neutron, a particle with almost exactly the mass of a proton but carrying no electric charge whatsoever. Neutral, as its name suggests. This was an enormous moment. It completed the basic picture of the atomic nucleus. Suddenly the arithmetic worked. Suddenly you could understand why atoms weigh what they weigh. Chadwick had found the missing piece, and the discovery was so important he'd earn a Nobel Prize for it just 3 years later. Now hold that date in your mind. 1932. The neutron is brand new. The ink is barely dry. Most physicists are still busy working out what this strange new neutral particle even does inside ordinary matter. And here's where it gets wonderful, because just 2 years later, a pair of astronomers looked at this freshly discovered particle and made a leap that frankly should not have been possible yet. Their names were Walter Baade and Fritz Zwicky. Baade was a careful, meticulous observer of the heavens. Zwicky was something else entirely. Brilliant, abrasive, wildly imaginative, the kind of mind that throws out 3 impossible ideas before breakfast and turns out to be right about one of them in a way nobody expected. And together, in 1934, they proposed something that sounded at the time like pure science fiction. They suggested that when a massive star dies and when it runs out of fuel and collapses, it might not simply scatter itself across space and vanish. Instead, they said the collapse might be so violent, so absolute, that it crushes the dying star's core down into something entirely new, a star made almost entirely of neutrons, those very same neutral particles Chadwick had only just discovered, packed together so tightly that the whole object would be the size of a small city, but way more than the sun, a neutron star. Think about how bold that was. The neutron itself was 2 years old. Nobody had the faintest idea how you'd ever see such a tiny, distant object. And here are two astronomers calmly predicting that the universe builds them, that they're out there, formed in the deaths of giant stars. They were, in a real sense, predicting something before anyone believed it could ever be observed. For decades, the idea sat there, clever, elegant, and almost entirely ignored. A beautiful theory with no way to test it. The kind of thing you mention as a curiosity and then move on from, because what could you possibly do with it? So let me tell you what actually happens when a great star dies, because Bade and Zwicky turned out to be right. And the process is one of the most dramatic things in all of nature. And yet, in its way, strangely peaceful, like a long breath finally let go. Picture a truly massive star, not one like our own sun, which is a gentle, middle-sized thing. Picture a giant, something between roughly 8 and 20 times the mass of the sun, or even more. For millions of years, a star like that lives in a kind of beautiful balance. Deep in its core, it's fusing light elements into heavier ones, and that fusion releases an enormous outward push of energy and pressure. That outward push fights against the star's own gravity, which is forever trying to pull everything inward and crush it. Pressure pushing out, gravity pulling in, held in a steady standoff. As long as the star has fuel to burn, it stays in balance. It holds its shape, it shines. But fuel runs out, it always runs out eventually. The star burns through its hydrogen, then its helium, then heavier and heavier elements, each stage faster than the last, working its way up the ladder. And at the end of that ladder, it reaches iron. Iron is special and a little sad in the life of a star, because iron is the place where fusion stops paying its way. Fusing iron doesn't release energy. It costs energy. So when the core fills with iron, the fire that's been holding the star up for millions of years suddenly has nothing left to burn. The outward push falters, and gravity, which has been waiting patiently this entire time, finally wins. What happens next happens fast, faster than you can really imagine. The iron core, which has been holding itself up against gravity, simply gives way and collapses inward. We're talking about a core larger than the Earth crashing down to something city-sized in a fraction of a second. And in that catastrophic squeeze, something remarkable occurs in the matter itself. The pressure becomes so extreme that the protons and electrons, those positive and negative particles that normally keep a polite distance from one another inside atoms, are crushed together. And when you force a proton and an electron into the same tiny space hard enough, they merge. The positive charge and the negative charge cancel out, and what you're left with is a neutron, that same neutral particle born now in unimaginable numbers in the heart of the dying star. Physicists call this inverse beta decay, which is a tidy name for a violent thing. It's the universe taking ordinary matter apart and rebuilding it into neutrons under the hammer of gravity. And in that merging, something else pours out. A flood of ghostly particles called neutrinos. Neutrinos are the shyest things in all of physics. They barely interact with anything at all, slipping through entire planets as though the planet weren't there. And yet so many of them are created in this collapse in such a sudden burst that they carry away an absolutely colossal amount of energy. A wave of these ghost particles surges outward through the dying star, and it's so dense, so overwhelming, that even these famously antisocial particles shove against the surrounding material on their way out. The collapse releases more neutrinos in a few seconds than our sun will give off in its entire lifetime. It's a quiet, invisible flood of energy, and it's part of what blows the rest of the star apart. Because here's the turn, the core collapses inward and then it stops. Suddenly, almost violently, the neutrons that have just formed pack together as tightly as the laws of nature will allow, and at nuclear density they refuse to be squeezed any further. The infalling matter slams into this suddenly rigid core and rebounds like a wave hitting a wall and crashing back. That rebound, helped along by the neutrino flood, blasts the entire outer body of the star outward into space in a colossal explosion. We call it a Type II supernova, a core collapse supernova. And for a few weeks, a single dying star can outshine an entire galaxy of 100 billion others. It's one of the brightest, most violent events the universe ever produces. And when the light finally fades, and the blown-off layers drift away into the dark to seed new stars and worlds someday, what's left behind in the quiet at the center is exactly the thing Bard and Zwicky imagined: a neutron star, the crushed, leftover core of the giant that died, a city-sized sphere of neutrons holding more mass than our sun, spinning in the silence where a star used to be. So that's the birth. That's where these strange objects come from. Out of the most violent death in nature comes one of the densest, stillest, most extraordinary objects in all of creation. There's something almost gentle in that when you sit with it. The fiercest explosion in the cosmos leaves behind a small, perfect, silent thing turning quietly in the dark. But knowing a thing can be born and actually finding one are two very different matters. And for more than 30 years after Bade and Zwicky's prediction, nobody found one. How could they? These objects are tiny by cosmic standards, only the size of a city, and dim and impossibly far away. You can't simply point a telescope and expect to see a glowing dot that's the diameter of, say, a single town, sitting 1,000 light years off in the dark. It would be like trying to spot a single candle flame on the far side of an ocean. The prediction was beautiful, but it seemed destined to stay just that. A prediction, untested, possibly untestable. And then came 1967 and a young researcher named Jocelyn Bell Burnell, and one of my favorite stories in all of science. Let me tell it to you slowly because it's the kind of story that deserves room to breathe. Jocelyn Bell Burnell was a graduate student working on a radio telescope, not the great dish you might be picturing. This was a sprawling field of wires and posts, acres of it, that she had actually helped to build herself, by hand, stringing the cables, hammering the posts. The telescope listened to the sky in radio waves rather than visible light, and it produced its readings as ink lines traced onto long rolls of paper, the way an old seismograph scratches out the trembling of the earth. And it was Jocelyn's job to go through those endless rolls of paper by eye, reading the squiggles, watching for anything strange. That is patient, painstaking, lonely work. Mile after mile of paper, day after day, the kind of task most people's eyes would glaze over within an hour. But she had the rare gift of really paying attention. And one night, buried in all that scribble, she noticed something odd, a tiny smudge of signal that didn't behave the way the usual cosmic static did. Most people would have dismissed it, a glitch, a bit of interference from a passing car, a television, some bit of human noise leaking into the wires. But it nagged at her. So she went back, and she looked closer, and she found something astonishing. The signal was pulsing, regular, steady. A sharp little pulse of radio energy arriving again and again, and the gap between the pulses was almost unbelievably precise, repeating roughly every 1⅓ seconds, ticking like the most accurate clock anyone had ever heard from the sky. It was so regular, so machine-like, so perfectly timed, that it genuinely unsettled the people who first saw it, because nothing natural was supposed to keep time like that. Stars don't tick. Galaxies don't pulse on a metronome. This was a heartbeat from deep space, steady as a clock, and at first, nobody had the faintest idea what could possibly be making it. In fact, and I love this, in those very first days, before they understood it, they only half-jokingly labeled the signal LGM-1, and LGM stood for Little Green Men, because the signal was so precise, so artificial seeming, that the possibility, however unlikely, flickered at the edge of everyone's mind. What if this was a message? What if something out there was deliberately sending a beacon, tick by tick, into the dark? They didn't really believe it. But the regularity was so uncanny that the joke wrote itself, and the name stuck, at least for a while. Of course, it wasn't Little Green Men. As more of these ticking sources turned up across the sky, the truth came into focus, and the truth was even more wonderful than the joke. What Jocelyn Bell Burnell had found was the long-lost object Bardi and Zwicky had dreamed up 33 years earlier. A neutron star, the first one ever detected. The precise ticking wasn't a message at all. It was the star spinning. These objects rotate often astonishingly fast, and they fire out beams of radio energy from their magnetic poles, like the rotating beam of a lighthouse sweeping across the sea. Every time that beam sweeps across the Earth, we catch a pulse. Tick. The beam swings away. Silence. The beam comes round again. Tick. A spinning city-sized neutron star sending us a flash with every turn. They came to be called pulsars, pulsing stars. And that very first one Jocelyn found was the proof, at last, that neutron stars were real. Not a chalkboard fantasy. Real objects scattered across the sky, ticking out their rotation for anyone patient enough to listen. It's one of the great discoveries of the 20th century. A prediction made before anyone thought it observable, confirmed decades later by a graduate student with the patience to read miles of paper and the sharpness to notice when something didn't fit. And here I have to add the part of the story that still sits a little uneasily with a lot of people, myself included. When this discovery was honored with a Nobel Prize in 1974, the prize went to others on the team. And Jocelyn Bell Burnell, who had built the telescope, read the data, and first spotted the signal that started it all, was not among those named. She has, by all accounts, been extraordinarily gracious about it over the years, far more gracious than I think I could ever manage. But it remains one of those moments that history quietly raises an eyebrow at. The person who first heard the heartbeat of a neutron star wasn't on the list. It's worth remembering her name tonight, Jocelyn Bell Burnell. So now, finally, we knew. Neutron stars were real. We could hear them ticking across the galaxy, thousands of them by now. We knew, roughly, how they were born. In the collapse and rebound of dying giant stars, we knew, roughly, what they were made of, neutrons, crushed to the density of an atomic nucleus. And we had that famous line, the sugar cube and the billion tons, to wave at people to make them gasp. But notice what we still didn't have. We could hear them. We could time their ticking down to fractions of a second, but we couldn't see one. Not really. We couldn't hold one up to the light and measure it. We didn't actually know, with any precision, how big one was. Was it 10 kilometers across? 15? 20? It mattered enormously because the exact size of a neutron star, how much mass is squeezed into how small a ball, is the single biggest clue to what's actually inside it, to the strange physics happening down in that crushed core. Squeeze the same mass into a smaller ball and you're telling a very different story about the matter at the center than if it spreads out a little wider. The size is the fingerprint of the interior, and for decades we couldn't read it. It was a frustrating place to be. We had these objects plainly real ticking away. We had elegant theories about their insides, beautiful competing theories, all making slightly different predictions. But we had no way to walk up and measure one and find out which theory the universe actually preferred. It was like knowing a sealed box exists, hearing it rattle, even knowing roughly how heavy it is, but never being allowed to open it, or even to wrap a measuring tape around the outside. We knew the neutron star was there. We just couldn't get its measure. And that is exactly where tonight's real story begins. Because not so very long ago, that changed. We finally found a way to do the impossible-sounding thing, to take an object the size of a city, sitting more than 1,000 light-years away, and actually measure how wide it is. Not estimate, not guess from theory, measure. And not only its size, but the shape of the glowing hot patches on its surface, and through them the secret architecture of its magnetic field. What we found when we finally took that measurement was so surprising, so contrary to what the textbooks had quietly assumed for half a century, that it sent physicists right back to their drawing boards. To do it, we'd build an instrument and carry it up above the atmosphere to ride along on the side of the International Space Station, 300 and more kilometers over your head, circling the Earth 16 times a day. We'd give it the patience to catch individual particles of X-ray light and stamp the arrival time of each one to within 100-billionths of a second. And we'd point it at a single tiny spinning star, and we'd watch the way its light flickered, and from that flicker, from nothing more than the rhythm and brightness of X-rays arriving from a city-sized speck 1,000 light-years off, we would, at last, read its true size. That instrument has a name, and the star it looked at has a name. And what they revealed together, a star about 12 kilometers across, with hot spots in all the wrong places, is where we're going next. But not quite yet. Let your shoulders drop a little first. There's no rush to get there. The star has been spinning for millions of years, and it'll go right on spinning whether we hurry or not. So let yourself sink a bit deeper into wherever you're lying, and just hold this in your mind as you drift. Somewhere out there, more than 1,000 light-years away, there's a perfect little sphere the size of a city, denser than the heart of an atom, turning silently in the dark. And for the first time in all of history, we found a way to reach across that impossible distance and take its measure. We'll begin to see exactly how in just a moment. Welcome to Calm and Clever. It's lovely to have you here tonight. Before we wander in any further, let me say a quiet thank you to those of you already drifting off to these little journeys. And if you're new, if you'd like more nights like this one, a gentle like and a subscribe really does help this small, sleepy channel keep going. Small creators like me lean on that more than you'd think. And while you're settling, I'd love to know, where in the world are you listening from tonight? What hour is it in your corner of the dark? You don't have to answer now. You don't have to do anything now. If you drift off before the end, that's perfectly all right. The star will still be here. The ideas will keep. So, let's go back gently to that famous line you've heard before. The one everyone reaches for first. A sugar cube of this stuff, they say, would weigh 1 billion tons. And it's a lovely line. It's just not the whole truth. And the part it leaves out is the part worth carrying into sleep. Because the density isn't one number, it's a slope. Out near the surface, the matter is heavy, yes, but not unimaginably so. Fall inward, though, and the weight climbs, and it climbs, rising by a factor of millions as you sink toward the middle. The average density across the whole star lands somewhere between 3.7 and 5.9 times 10 to the 17th kilograms in every cubic meter. For comparison, the density packed inside the nucleus of an ordinary atom, the very heart of matter as we usually meet it, sits around 2.3 times 10 to the 17th. So a neutron star isn't merely as dense as an atomic nucleus. On average, it's a little more. And right down near the core, it leaves nuclear matter far behind. The billion-ton sugar cube is real, but only if you scoop it from near the center. Closer to the crust, it's far lighter. The cliché, it turns out, was just standing at the front door, never quite stepping inside. Now, before we go reaching for that interior, let's set the scene the way the early scientists found it, because the strangest part is that this object was dreamed up before anyone thought they'd ever lay eyes on one. In 1932, a physicist named James Chadwick discovered the neutron, a particle with no electric charge at all, tucked into the nucleus alongside the protons, a quiet little discovery in its way. And just 2 years later, two astronomers named Walter Baade and Fritz Zwicky put forward an idea so bold it almost sounds like a guess made in the dark. They suggested that when a truly massive star died, it might collapse into a ball made almost entirely of these newly found neutrons. A neutron star, predicted, you understand, before anyone had the faintest idea how you'd ever see such a thing. And here's the picture they were painting. Take a star far heavier than our sun, somewhere between 8 and 20 times its mass, sometimes more. For most of its life, it burns steadily, fusing lighter elements into heavier ones, building up an iron core at its heart. But iron is where the burning stops paying its way. The core can hold itself up no longer. Gravity wins. And in a fraction of a second, that core falls inward on itself. As it crushes down, something remarkable happens to the matter inside. The protons and the electrons are pressed so violently together that they fuse, each pair merging into a single neutron. We call this inverse beta decay, and it releases an almost unthinkable flood of ghostly little particles called neutrinos, a burst so vast it carries away most of the energy of the entire collapse. The infalling core keeps crushing until it reaches the density of an atomic nucleus, and there suddenly it can't squeeze any further. It stiffens, it rebounds, and that rebound, that bounce from the heart of a dying star, helps blow the outer layers off into space in one of the brightest explosions the universe knows, a Type II supernova. The light of it can outshine an entire galaxy for weeks, and left behind in the quiet afterward sits the thing that didn't blow away, the collapsed core, the neutron star. So that's the theory, sketched out in the 1930s, a beautiful idea with no proof. And for a long while, that's all it was, until a night in 1967. A young researcher named Jocelyn Bell Burnell was poring over data from a radio telescope, long ribbons of paper, line after line of squiggles, hunting for something amid all the noise. And she found a signal that shouldn't have been there. A pulse, steady, regular, ticking like a metronome, arriving again and again with an almost machine-like precision. Nothing natural was supposed to keep time that perfectly. For a little while, only half joking, they labeled it LGM1, Little Green Men. Because if you'd never seen one before, a signal that regular might just look like someone somewhere trying to say hello. It wasn't a message, of course. It was something stranger and, in its way, more wonderful. It was a neutron star, spinning, sweeping a beam of radio light across the Earth with every rotation. The very object Baade and Zwicky had imagined 3 decades earlier, now waving at us across the dark. A pulsar, we'd come to call it. The prediction had come true. And there's a quiet, uncomfortable note tucked into that triumph, one worth holding gently. When the Nobel Prize was awarded for this discovery in 1974, Jocelyn Bell Burnell, the one who first spotted that strange little pulse in all those reams of paper, was not among those honored. The prize went to others. It's one of those moments the history books have been arguing about ever since. But here's where the story turns toward our own time. For all those decades, from the first prediction, through that first ticking signal, through everything we learned about how these stars are born and how they spin, there was still one thing we could not do. We could weigh them roughly. We could time their pulses, but we could not truly measure one. We could not say with confidence exactly how big across one of these things actually is. We couldn't take a ruler to a star 1,000 light years away that's only the size of a city. And then finally we built something that could. It didn't guess. It didn't estimate from afar and call it close enough. It measured. A star the size of a city read at last. We'll see exactly how very soon. So let's talk about how you actually measure something like that. Think about what we're asking for a moment. A neutron star sits somewhere between roughly 1,000 and 100,000 light years away, depending on which one you're looking at. It is, at most, about 24 kilometers wide. That's the size of a city, a small city. And it doesn't emit the kind of light your eyes could use. It glows in X-rays, radiates in radio waves, pulses and spins and sings in frequencies we have to build special ears to hear. So how do you put a measuring tape around something like that? How does a species still figuring out how to live peaceably on one small planet manage to determine the actual physical diameter of a collapsed stellar core 1,000 light years away to within a kilometer? The answer is both deeply clever and a little poetic, and it involves a piece of hardware bolted onto the outside of the International Space Station, a technique borrowed from the geometry of bent light, and a team of scientists who were willing to time X-ray photons to 100-billionth of a second. 100-billionth, 100 nanoseconds. That is roughly the time it takes light to travel about 3 centimeters, and that level of precision is exactly what the measurement required. The instrument is called NISA. The name stands for Neutron Star Interior Composition Explorer, which is one of those backronyms that scientists work very hard to make satisfying, and this one largely succeeds. It's a NASA mission, and it lives right now attached to the exterior of the ISS, looking outward into the universe while astronauts go about their routines a few meters inside. It was installed in June of 2017. If you've ever looked at images of the space station and noticed a boxy, somewhat ungainly-looking instrument package clinging to one of the truss segments, pointing at the sky, there's a reasonable chance that's NISA or something near it. Inside NISA is the X-ray timing instrument, which its builders sometimes call the XTI. And the XTI is built around 56 X-ray concentrators. Imagine 56 small, precisely shaped optical systems, each one gathering incoming X-ray photons and directing them toward silicon drift detectors sitting at their focal points. Silicon drift detectors are a kind of technology that can register a single X-ray photon arriving and note the exact moment of its arrival with extraordinary precision. The whole ensemble is designed to do one thing supremely well: clock the precise arrival time of individual X-ray photons coming from a spinning neutron star, again and again and again, building up a picture of how the brightness varies as the star rotates. Now, why X-rays? Neutron stars are hot, extraordinarily hot, particularly those that have only recently formed, but even older ones maintain surface temperatures of around 1,000,000 Kelvin. At those temperatures, the dominant radiation isn't visible light, it's X-rays. The surface glows in X-rays the way a coal glows in visible red light. except the coal is a stellar remnant the size of Manhattan, and the glow would kill you from a considerable distance. But for NICER, this is ideal. X-ray photons carry enough energy that each one registers clearly individually, and the arrival time of each can be pinned down to within that 100 nanosecond window. But timing X-ray photon arrivals is only half of it. Here's where the real ingenuity comes in, and where I want you to slow down with me and follow the logic carefully, because it's beautiful. Some neutron stars spin very fast, extraordinarily fast in fact. A class called millisecond pulsars can spin hundreds of times per second. They complete hundreds of full rotations in the time it takes you to blink. PSR J0740+0451, which became NICER's first major target, spins roughly 205 times every second. Now imagine a star spinning that fast, and somewhere on its surface, perhaps near a magnetic pole, there is a patch that is hotter than the surrounding surface, a hot spot. As the star spins, that hot spot rotates into your line of sight, and then back out again, over and over 205 times per second. Each time it faces you, you receive a pulse of X-ray brightness. Each time it rotates away, the brightness drops. You build up what's called a pulse profile, a map of how the brightness rises and falls with each rotation. Now here is where Albert Einstein enters quietly and does something useful. The gravity near a neutron star's surface is enormous, 200 billion times stronger than Earth's. At that level of gravitational intensity, space-time itself is dramatically curved, and that curvature does something remarkable to light. It bends it. Any photon traveling near a neutron star, even a photon trying to leave the surface and head out into space, follows a curved path, not a straight line, a curve bent by the gravity of the star it's trying to escape. And here is the consequence that NICER exploits. If the gravity bends light, then you can see more of the star than you'd expect. On an ordinary object with weak gravity, you can only see the hemisphere facing you. The back is hidden, but on a neutron star, light from regions that are technically on the far side gets bent around the edges, curving toward your instruments. You can see, depending on the exact mass and radius of the star, something like 60 to 70% of the star's total surface at once, or even more. Parts of the far side are literally bent into view. This sounds like a curiosity, but it's a measurement tool, because the amount of bending depends on the compactness of the star, on the ratio of mass to radius. A star that is very compact, high mass, packed into small radius, bends light more aggressively. A star that is less compact bends it more gently. And that difference in bending leaves a fingerprint in the pulse profile, the shape of the brightness curve, how quickly it rises, how long the hot spot stays in view, how the brightness falls and flattens, encodes information about how much of the far side is being bent into view, which encodes information about the star's compactness, which, if you know the mass independently from orbital mechanics or other means, gives you the radius. This technique is called pulse profile modeling. You take the observed brightness curve, you write down the equations of general relativity that govern how light bends in curved space-time, and you fit a model to the data. The model has three parameters: the mass of the star, the radius of the star, the positions and sizes of the hot spots. You adjust those parameters until your model's predicted pulse profile matches what NICER actually observed. And when it matches, when theory and measurement agree, the values of those parameters are your measurement. You have weighed and sized the star. The elegance here deserves a moment of appreciation. You are not pointing a ruler at a star 1,000 light-years away. You are using the star's own gravity as a lens, reading the curvature of space-time in the arrival times of X-ray photons, and working backward from the shape of the light curve to the physical parameters of the object producing it. You are, in a sense, letting Einstein's equations do the measuring for you. This is not a simple calculation. Fitting a pulse profile from a rapidly spinning neutron star requires integrating general relativistic, light-bending equations across the entire stellar surface, accounting for the Doppler shift of photons emitted from the approaching and receding limbs of the spinning star, and exploring an enormous space of possible mass-radius combinations to find the ones that fit the data. It took teams of specialists, years of analysis, and sophisticated Bayesian statistical methods to do it properly. 2 independent teams tackled PSR J0030+0451 simultaneously, working from the same nicer data but using different analysis pipelines, different statistical frameworks, somewhat different hotspot models. This was deliberate. You want independent groups to arrive at the same answer, because if they do, you can have genuine confidence. One team was led from Amsterdam. Their results are often cited as Riley et al. The other was led from Maryland, Miller et al., both published in December of 2019 in the Astrophysical Journal Letters. Both found that J0030+0451 has a mass somewhere around 1.3 to 1.4 solar masses and a radius right around 12 kilometers. Riley's team gave approximately 12.71 kilometers. Miller's team gave approximately 13.0 kilometers. There it was. Not a guess, not a theoretical estimate, not a range plucked from a model of nuclear physics. A measurement. The diameter of a neutron star in kilometers, pinned down to the sort of precision that makes it feel real in the way that 1 billion tons per cubic centimeter somehow never quite does. 12 kilometers. Stop and think about that for a moment if you can. 12 kilometers? If you've ever driven on a motorway, 12 kilometers is a stretch you might cover in perhaps 7 minutes at a comfortable speed. If you've ever walked in a city, 12 kilometers is the distance from a downtown core to the outskirts. It is, as these things go, not very far at all. And inside that 12-kilometer sphere is packed approximately 1.4 times the mass of our Sun, which is about 4 million kilometers wide, compressed by a factor of 100,000 in each direction, compressed until 12 kilometers is all that's left. That's the real-world consequence of the measurement. It's not just a number, it's a scale that the human mind rebels against slightly, the way it always does when confronted with genuinely extreme physics. But now it's not a theoretical prediction. It's something someone clocked with an instrument bolted to the outside of a crewed space station by reading bent light. There was just one problem, a very beautiful, very surprising, very informative problem, one that rewrote the textbook picture in a way no one was quite expecting. Here is what the textbook said for a long time. A neutron star has a magnetic field. In fact, it has an extremely powerful magnetic field because the star that formed it had a magnetic field, and when that star's core collapsed from something sun-sized down to something city-sized, all that magnetic flux was compressed into a tiny space. The field lines squeezed together and amplified enormously. The textbook picture of that magnetic field was simple, a dipole, like a bar magnet. 2 poles, north and south, roughly opposite each other. The star spins. The magnetic axis is tilted slightly relative to the rotation axis, so the poles sweep around as it rotates. And the hot spots, the places where magnetic field lines converge on the surface and funnel energetic particles downward, heating the surface locally. Those hot spots sit at the magnetic poles. 2 spots, one roughly north, one roughly south, roughly on opposite sides of the star. Clean, symmetric, intuitive, that was the picture. NICER looked at J0030+0451 and said, in the politest scientific language available, not quite. The hot spots this star's surface actually shows, the things that produce the observed pulse profile, are not two neat antipodal circles sitting on opposite ends of the star like the north and south poles of a bar magnet. They're not even in opposite hemispheres. Both hotspots, both of them, appear to sit in the southern rotational hemisphere of this star. And they're not simple circles. The models that best fit the data require oddly shaped regions, elongated patches, crescents, oval smears, stretched in ways that a simple dipolar field wouldn't produce. One spot, in the best-fitting models, is relatively small and circular. The other is larger, more complex, possibly crescent-shaped. And they're roughly in the same part of the sky as seen from the star. The same hemisphere, tucked together like a couple of footnotes when the textbook expected them to be written on opposite pages. This result, which appears in work by Billis and colleagues in 2019 alongside the main Riley and Miller analyses, is not a small correction. It's a fundamental revision to what we assumed we knew about neutron star magnetic fields. If the hotspots don't sit at the poles of a simple dipole, then the magnetic field is not a simple dipole. It's something messier, something more complex, with higher order structures, multipolar components, field lines curling and looping in arrangements that don't reduce to a clean bar magnet picture. And then in 2021, when the analysis was revisited with additional data from the XMM Newton Space Telescope combined with the NICER observations, things got even stranger. The new analysis raised the possibility, not yet a certainty, but a genuine possibility, that J0030+0451 might have a third hot spot, a third hot region on this star's surface, not accounted for in the original two-spot models. Now, if you're resting comfortably somewhere, perhaps letting this wash over you as you drift towards sleep, the detail of whether there are 2 or 3 hotspots might feel like a technical footnote. But I want to linger here a moment because it matters more than it sounds. The geometry of the hotspots tells you the geometry of the magnetic field. The magnetic field tells you what's happening inside the star, in the outer layers and perhaps deeper, because the field threads through the star and the processes in the crust and perhaps the core shape and maintain that field. If the field is not a simple dipole, it means the processes that generated it and sustain it are not what we thought. It means the star's interior is doing something more complicated than the simplest models assumed. The magnetic architecture of a neutron star is a window into its interior structure. And that window just got a lot less straightforward to look through, which raises a question worth sitting with for a moment. If the textbooks got the magnetic field wrong, if the poles aren't where we thought, if the spots are crescents in one hemisphere instead of circles at opposite ends, then what else did the textbooks oversimplify? The bar magnet dipole was a foundational assumption underlying decades of pulsar models. If it's not quite right for J0030, might other assumptions be similarly approximate? Might our picture of the crust, of the deep interior, of what happens to matter at these densities, might those pictures also be more complicated than the clean textbook version? That question is not rhetorical. It's the thing physicists working on neutron stars are actively wrestling with right now. And it's one reason the NICER measurements are generating so much excitement, because they're not just confirming theory, they're finding genuine surprises that push the theory forward. And here's what's lovely about being in this particular moment in the history of the science. We didn't just measure J0740+0451, we kept going. NICER turned its attention to other neutron stars and began building up a picture, a sample, a set of real-world measurements rather than a single data point. The second major NICER result came from a very different kind of star. PSR J0740+6620 is, at the time of its measurement, the most massive neutron star whose mass had been precisely pinned down, about 2.8 solar masses, not 1.4, not 1.5, 2 and a bit. Half again as massive as J0030+0451. This is a substantially heavier object. Your intuition, shaped by everyday experience with dense objects, might tell you that a heavier version of something should probably be bigger. A heavier ball is usually a larger ball. A heavier planet is usually a larger planet. Your intuition in this case is gently but completely mistaken. When the teams analyzed NICE's data on J0740+6620 using both the NICE observations and combined data from XMM Newton, and ran the same pulse profile modeling that had worked so beautifully for J0030, they found a radius of approximately 12.4 kilometers. Riley and Miller's respective teams produced consistent results, both published in 2021, 12.4 kilometers. Compare that to J0030+0451's radius of about 12.71 kilometers. Add 50% more mass to a neutron star and the radius barely changes. These two stars, one carrying 1.3 to 1.4 solar masses and one carrying 2.08 solar masses, are essentially the same size. 12 kilometers across, give or take a small fraction. Pack in more mass and the star doesn't expand, doesn't even stay the same size while getting denser, in the way a balloon stays the same size as you squeeze it. It is, as measured, almost stubbornly constant in its dimensions. You add mass, the radius doesn't grow, and so the interior simply becomes denser. More mass, same space, higher density. This is profoundly strange, and it tells you something fundamental about what's holding this star up. In an ordinary star, would like the Sun, gravity is balanced by thermal pressure. The nuclear fires in the core generate heat and light, and the outward pressure of that radiation and that hot gas pushes back against gravity. Take away the fire and the star collapses. A neutron star has no fire. It's not fusing anything in its core, or rather, not in the conventional sense. What holds it up is something else entirely, something quantum mechanical. The outer layers of a neutron star are supported partly by something called electron degeneracy pressure, the same quantum mechanical principle that holds up white dwarfs. But go deeper, where the electrons are all gone and you have a dense fluid of neutrons, and the support comes from neutron degeneracy pressure, together with the effects of the strong nuclear force operating at these extreme densities. These are quantum effects, not thermal ones. They don't depend on temperature. The star can cool to absolute zero and the pressure remains. The resistance comes not from heat, but from the fundamental quantum constraint that two neutrons cannot occupy the same quantum state in the same place, a principle called the Pauli exclusion principle, and from the repulsive component of the strong nuclear force that kicks in when nucleons are packed very close together. At moderate densities, which is to say, at densities typical of the outer and middle parts of a neutron star, this repulsion gives the star a certain stiffness. The nuclear matter behaves in the language of the field as a stiff equation of state. And a stiff equation of state produces a compact star that resists compression. Add mass, and the pressure ramps up quickly, preventing the star from shrinking much. That's why J0740 with 50% more mass than J0030 is only very slightly smaller in radius. The interior pressure-density relationship is steep enough that the extra mass simply raises the internal pressure, holding everything at nearly the same size. And then NICE gave us a third data point, which arrived quite recently. In 2024, a team led by Choudhury published measurements of PSR J04374715. J0437 is particularly special because it's the nearest and brightest millisecond pulsar we know of, only about 510 light-years from Earth, which is extremely close on cosmic scales, making it a particularly rich target for NICE's instruments, for a mass of approximately 1.4 solar masses, a fairly typical neutron star mass. The measured radius came out to approximately 11.36 kilometers. 11.36. 3 neutron stars, 3 independent measurements, all clustering around 12 kilometers. Different masses, 1.4 and 1.4 and 2.08 solar masses, but all broadly similar in size. The universe, it seems, has a preferred radius for neutron stars, and that radius is roughly that of a city. We are not just theorizing this anymore. We have measured it. But there is a ceiling, a hard ceiling. And it's worth understanding what that ceiling is, because it marks the place where all of this, all the quantum pressure, all the nuclear stiffness, all the extraordinary resistance to compression that lets a star carry 2 solar masses in 12 kilometers, finally gives way. That ceiling is called the Tolman-Oppenheimer-Volkoff limit, the TOV limit. It's named for 3 physicists, Richard Tolman, J. Robert Oppenheimer, yes, the same Oppenheimer, and George Volkoff. And the story of how this limit was first calculated is itself a small cautionary tale about the danger of getting the physics slightly wrong and then presenting a number with great confidence. The year was 1939. Oppenheimer and Volkoff published a paper in Physical Review in which they set out to answer a specific question. How massive can a neutron star be before its own gravity overwhelms all pressure and it collapses? They wrote down the equations of general relativity governing how pressure and gravity balance inside a compact star. These are the equations that Tolman had also been developing, which is why his name is attached. They assumed the matter inside the star was composed of neutrons. They included degeneracy pressure. They solved the equations, and they got an answer, roughly 0.7 solar masses. Below 0.7 solar masses, a neutron star could be stable. Above 0.7 solar masses, gravity would win and collapse would follow. That number was wrong, off by a factor of about 3. Not because the mathematics was faulty. The mathematics was correct given the model. The problem was the model. Oppenheimer and Volkoff omitted the strong nuclear force. They treated the neutrons as a simple degenerate gas and ignored the repulsive component of the nuclear interaction that kicks in at high density and stiffens the matter considerably. This isn't really their fault. In 1939, the detailed structure of the strong nuclear force was not yet understood, but the consequence is that their calculation underestimated how stiff nuclear matter is, and therefore underestimated how much mass the pressure could support. Include the real nuclear physics and the mass limit jumps dramatically upward. Modern estimates of the TOV limit, incorporating everything we've learned about nuclear forces and constrained by actual observations, place it around 2.2 to 2.3 solar masses. Some analyses cluster around 2.17 solar masses. This is still somewhat uncertain because it depends on the equation of state of dense nuclear matter, which is, as you will discover when we fall deeper into this story, not fully known. But this limit, wherever exactly it falls, is absolute in a way that feels almost philosophical. It is not a practical limit, the kind you can engineer around if you're clever enough. It's a limit rooted in the fundamental laws of physics. Below the TOV limit, quantum pressure holds. Above it, gravity wins. Unconditionally, without exception. And when gravity wins, there is no stable state for the star to settle into. It continues to collapse. The density increases without bound. And what you are left with is something that is no longer a neutron star, something that is no longer any kind of normal matter at all. You are left with a black hole. There is a precise weight, something in the neighborhood of 2.2 times the mass of our sun, at which a neutron star cannot survive. Not if you made it out of the hardest material in the universe, not if the physics cooperated in every way it possibly could. At that weight, existence as a neutron star simply ends and something else begins. The fact that we found neutron stars at 2.08 solar masses, so close to that ceiling, means we are observing objects that are living very close to the edge. And the question of exactly where the edge is was sharpened significantly by an event that took place in 2017, not with NASA, with a completely different kind of instrument, a different kind of detection, listening for a different kind of signal entirely. On August 17, 2017, the LIGO and Virgo gravitational wave detectors picked up a signal that was different from any they had heard before. Previous detections had been mergers of black holes, two massive, dark objects spiraling together in the final moments before collision, sending ripples through space-time that propagated outward at the speed of light and arrived at Earth as the faintest imaginable vibration, a stretching and squeezing of space so small that the detectors were registering displacements thousands of times smaller than a proton. Those black hole mergers had been remarkable. But this was something else. This signal, called J0740+0620, had the signature of two neutron stars spiraling together. Two city-sized objects, each carrying about 1 to 2 solar masses, each spinning and orbiting the other in a death spiral, radiating gravitational waves and losing energy until the distance between them shrank to zero and they merged. The merger produced a gravitational wave signal that LIGO and Virgo both detected. It also, crucially, produced an electromagnetic signal, a burst of light in multiple wavelengths that was observed by telescopes around the world and in space. For the first time in history, we were watching the same cosmic event in both gravitational waves and light simultaneously. That event, J0740+0620, was extraordinary in many ways, but one of its contributions to the story of neutron stars was this. The combined mass of the two merging stars was known from the gravitational wave signal, and the question of whether the resulting merged object promptly collapsed into a black hole or briefly survived as a hypermassive neutron star before collapsing, or somehow survived longer. That question was answerable, at least in rough terms, by watching what the light afterward looked like. The analysis, carried out by teams including Margalit and Metzger, and Rezolla and others, used the J0780+17 outcome to sharpen the estimate of the TOV limit. If the remnant collapsed relatively promptly, the total mass gives you an upper bound on the TOV limit. The result was consistent with a maximum around 2.17 solar masses, though different analyses gave slightly different numbers, all clustering in that 2.2 to 2.3 range. So we now have the TOV limit not just from theory, but from watching a neutron star try to exceed it. We watched two neutron stars collide, we watched what happened to the combined mass, and from that we sharpened our understanding of where the hard ceiling sits. Above 2.2 solar masses or thereabouts, perhaps 2.3, depending on the nuclear physics, there is no floor. Nothing holds, the star falls forever. And we know this now not from equations alone, but from listening to the sound of two stars running into each other across the universe. It is, if you let yourself feel it, a remarkable kind of knowledge. We built instruments sensitive enough to detect the tremor of a collision 30 million light-years away. We did it not once, but repeatedly. And from those tremors, we deduced a hard constraint on the maximum mass of the densest stable objects in the universe. There are stars out there, right now, orbiting companions, slowly gathering mass, creeping toward that ceiling. When they cross it, they will cease to exist as neutron stars and become black holes, silently, instantly, completely. And we now know more precisely than before exactly where that transition occurs. But all of this, the measurement of the radius, the size, the mass limit, all of this is in some sense external. It tells you about the star from the outside, the radius, the mass, the surface, hotspots, what you cannot measure directly, what no instrument can observe with a clean line of sight, is the interior. What is actually happening in there, layer by layer, from the thin wisp of an atmosphere down to the absolute center? For that, you need a different kind of reasoning. You need to take what you know, the measured radius, the measured mass, the behavior of matter at extreme densities from nuclear physics experiments here on Earth, the observations of how neutron stars cool and spin and occasionally shake, and build a picture. An inferred picture, but one grounded in real physics and constrained at every step by real measurements. So let's fall inward. Let's start at the surface and work down toward that unknown center, passing through the layers one by one, and I'll tell you at each step, not just what we think is there, but how we know it and how confident we are. At the very surface, or at the outermost shell, is the atmosphere. It is extraordinarily thin. We're talking about centimeters, perhaps tens of centimeters. In a terrestrial analogy, it's thinner relative to the star than the finest coat of paint relative to a billiard ball. And yet it matters enormously because this is where the star's spectrum forms, where the X-ray light that NICER detects originates. The atmosphere is likely composed of hydrogen, helium, or carbon, depending on the star's history. A light element plasma pressed to extraordinary density by the gravity beneath it, stretched thin by the same gravity pulling everything downward. This is the face the star shows to the universe. Below it, the real interior begins. The first solid layer is called the outer crust, and calling it solid is, in this case, not a metaphor. It's a crystalline lattice of atomic nuclei arranged like a regular grid, immersed in a sea of electrons that flow freely between them. Imagine ordinary metal, which has something like this structure. Positively charged atomic cores in a regular array, with conduction electrons flowing between them. Now compress that metal to a density that exceeds anything ordinary matter can achieve, where the nuclei are being held in their positions not by ordinary chemical bonds, but by the balance between their mutual repulsion and the pressure bearing down on them from all sides, and where the electron sea is not a mild quantum effect, but the dominant source of pressure holding the structure up. That is something like the outer crust of a neutron star. And as you go deeper, something begins to happen to the nuclei themselves. Deeper in the crust means higher pressure and higher density. Under that increasing pressure, the nuclei, already neutron-rich, containing more neutrons than protons in a ratio far beyond anything stable on Earth, get pushed to accommodate more and more neutrons. Nuclei that would be violently radioactive in a terrestrial laboratory are held together here by the surrounding pressure, stable only because the environment forces them to be. But there is a limit to how many neutrons a nucleus can absorb and still hold together, even with all that pressure. And when that limit is reached, at a density of roughly 4 times 10 to the 11th grams per cubic centimeter, the nuclei simply cannot hold any more neutrons inside themselves. The additional neutrons have nowhere to go but out. They drip. They literally leak out of the nuclei and form a separate, free-flowing fluid existing alongside the nuclear lattice. This transition has a name. It's called neutron drip, and it marks the boundary between the outer crust and the inner crust in a way that is as precise and real as any phase boundary in ordinary chemistry. Below the neutron drip line, you have a different kind of matter, not just a lattice of increasingly neutron-rich nuclei, but a lattice of nuclei coexisting with a quantum fluid of free neutrons flowing between them. We haven't sampled this material, we can't, but the physics that predicts it is the same physics that describes heavy atomic nuclei here on Earth, tested in accelerators, confirmed in terrestrial experiments. The neutron drip line is not a speculation. It is a consequence of the same nuclear physics we use every day, applied to the extreme conditions that prevail a few hundred meters below a neutron star's surface. And then, continuing downward, you hit something even stranger. The inner crust in the region just below the neutron drip line is a place where the rules that govern the shapes of atomic nuclei begin to break down in a way that no terrestrial experiment has ever replicated. Here, the density is climbing towards something called nuclear saturation density, approximately 2.3 times 10 to the 14th grams per cubic centimeter. Roughly the density at which the protons and neutrons inside an ordinary atomic nucleus are packed. As you approach that threshold from above, something remarkable happens to the nuclei themselves. In ordinary matter, nuclei are spherical, or close enough to it. The nuclear force, the strong force that binds protons and neutrons together, is short-ranged and fairly isotropic, and the electrostatic repulsion between protons pushes outward in all directions, and the result is a roughly round blob of nuclear material. That's what a nucleus looks like in a chemistry lab, in a medical scanner, in every context we have ever directly studied. But in the inner crust of a neutron star, the nuclei are so large, so neutron-rich, and so densely packed that they begin to interact with each other across the spaces that separate them. The free neutron fluid that surrounds them is no longer a background, it's a participant. And as density rises, the competition between two forces, the nuclear attraction that wants to pull all this material together, and the electrostatic repulsion between the protons that wants to push it apart, begins to carve the nuclear material into shapes that have no counterpart anywhere else in the universe. The physics community, with a certain affection for the subject, gave these shapes names drawn from Italian cuisine. At slightly lower densities, the nuclei are still roughly spherical, the gnocchi phase, named for small round pasta dumplings. As density rises, the spheres start to merge and elongate into long cylinders, filaments of nuclear material stretching through the neutron fluid. Spaghetti. Higher still, the cylinders flatten into broad sheets, like stacked sheets of pasta. Lasagna. And then the geometry inverts. Instead of nuclear material forming shapes in a neutron sea, it's the neutron fluid that forms cylindrical tubes and spherical bubbles inside a continuous sheet of nuclear matter. The anti-pasta phases, sometimes called anti-spaghetti and anti-gnocchi. Collectively, all of these exotic structural phases are called nuclear pasta. And nuclear pasta is not merely a curiosity. It is, according to the calculations done by Matthew Kaplan and Charles Horowitz and their collaborators, the strongest known material in the universe, stronger than diamond by an almost incomprehensible margin, stronger than the densest terrestrial alloys. The simulations, molecular dynamics calculations run in 2015 and refined afterward, estimate that nuclear pasta is approximately 10 billion times stronger than steel. 10 billion. Let that sit for a moment. If you wanted to break a piece of nuclear pasta, to fracture it, to crack it the way you might crack a crystal, you would need to apply a stress that no material in the observable universe other than nuclear pasta itself could withstand. It is self-referentially extreme. The strongest thing we know of is strong enough to resist forces that would shatter anything else. And it exists in a layer, the inner crust, that is perhaps a kilometer or two thick, wrapping the entire star, unseen and unmeasurable by any telescope we have yet built. We know it's there because the physics demands it, because the same equations that describe the nuclei we study in accelerators here on Earth, pushed to their extremes, predict this layered crystalline architecture, and because, as we will come to in a moment, we can see evidence of this crust fracturing when neutron stars shake. But before we get to that, there is another boundary to cross. Below the nuclear pasta region, the density finally reaches nuclear saturation density. The nuclei dissolve entirely, there are no more discrete nuclei, there is no more lattice. You have crossed into the outer core, and here the matter is a uniform quantum fluid, a dense soup of free neutrons with a small admixture of protons, electrons, and muons. And this soup behaves in ways that are, even by neutron star standards, deeply strange. Now, hold that picture for a moment at the outer core, a neutron fluid stretching from just below the crust down through perhaps 8 or 9 kilometers of the star's radius. And here is the thing about PSR J0740+6620 that stops physicists in their tracks. PSR J0740+6620 is a pulsar, a millisecond pulsar spinning several hundred times per second, located a few thousand light-years away in the constellation Camelopardalis. It was discovered in 2019, and it is remarkable for one reason above all others. It is the most massive neutron star whose mass has been precisely measured. Its mass is approximately 2.8 times the mass of the Sun, 2.08 solar masses, packed into a neutron star. Remember the first star we talked about, PSR J0740+0451, with its lopsided crescent hotspots and its mass of roughly 1.3 to 1.4 solar masses. NASA measured it at a radius of about 12.71 kilometers, a city a dozen kilometers across. Now here is PSR J0740+6620 with roughly 50% more mass, nearly half again as heavy. And NASA, working in combination with another telescope, the XMM Newton Space Observatory, to get enough X-ray counts to constrain the pulse profile, measured its radius, approximately 12.4 kilometers, the same, essentially the same size. A star with 50% more mass fits into almost exactly the same sphere. You add half again as much material, more than half a solar mass of additional matter, and the radius barely moves, a few tenths of a kilometer. Within the measurement uncertainties, these two stars, carrying wildly different masses, occupy essentially the same volume. And then in 2024, a team led by Partha Chowdhury published NICE's measurement of a third target, PSR J04374715, the nearest and brightest millisecond pulsar, just about 5-10 light-years away, close by neutron star standards, with a mass around 1.4 solar masses. Its measured radius came in at approximately 11.36 kilometers, a bit smaller than the previous two measurements, still consistent with the emerging picture, and still roughly the size of a city. Still 12-ish kilometers, give or take. Three different neutron stars, a range of masses from about 1.4 up to 2.08 solar masses, and all three have radii clustering around 10 to 13 kilometers. This is not what you might intuitively expect. If you have a ball of gas, like a regular star, and you add more gas to it, it gets bigger, bigger mass, bigger radius. That's the regime where pressure from hot, expanding gas holds the star up. And more gas means more pressure, means more volume. But that intuition completely fails here. What's holding a neutron star up is not heat. It's not gas pressure in the ordinary sense. It is quantum mechanical pressure. Two distinct kinds of it working together. The first is called degeneracy pressure. It arises directly from the Pauli exclusion principle, one of the foundational rules of quantum mechanics, which says that no two identical fermions, no two particles of the same type with the same quantum numbers, can occupy the same quantum state at the same time. Neutrons are fermions. In the crush of a neutron star's core, all the lowest energy quantum states are already filled. Every neutron is occupying a quantum state, and there are no empty lower states to fall into. The neutrons resist being compressed further, not because they're hot, not because they're bouncing around energetically, but because quantum mechanics simply refuses to allow them to share a state. They push back. And this quantum mechanical stubbornness is what we call neutron degeneracy pressure. This was the pressure that Oppenheimer and Volkoff were thinking about in 1939, when they wrote the paper that founded the theoretical study of neutron stars as physical objects. J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student George Volkoff, building on earlier work by Richard Tolman, calculated the maximum mass that neutron degeneracy pressure alone could support. Their answer, published in the March 1939 issue of Physical Review, was approximately 0.7 solar masses. Less than 1 solar mass. That number is wrong. Not a little wrong. Wrong by a factor of roughly 3. And the reason it's wrong is both simple and deeply revealing. Oppenheimer and Volkoff did not know about the strong nuclear force, or rather, they knew nuclei existed, but the detailed theory of the force that holds protons and neutrons together inside nuclei, the strong nuclear interaction and its behavior at high densities was not yet understood in 1939. Their calculation treated neutrons as though they were essentially free particles, interacting only gravitationally and subject only to quantum degeneracy pressure. A neutron star in their model was a very dense ball of nearly non-interacting neutrons, but that's not what neutron star matter is. At the densities prevailing in the outer core, above nuclear saturation density, in that dense neutron soup, the neutrons are not free. They are close enough together that the strong nuclear force acts between them, and the strong nuclear force at these densities is repulsive. Neutrons that are packed together past a certain point push back against each other through the strong force, not just through quantum mechanical exclusion. This additional repulsion, called the nuclear equation of state, or more specifically, the stiffness of the nuclear equation of state at high densities, is what raises the maximum supportable mass from Oppenheimer and Volkoff's 0.7 solar masses to somewhere around 2 to 2.25 solar masses. The strong nuclear force is the missing ingredient that Oppenheimer's calculation didn't have, and correcting for it doesn't just tweak the answer, but it triples it. The founding calculation was off by a factor of 3, which is, in its way, a beautiful thing, not a failure, a lesson. The physics of 1939 was as precise as it could be. Oppenheimer and Volkoff used everything that was known. They built the framework. And then the next several decades of nuclear physics, of experiments in accelerators, of scattering measurements and nuclear structure theory, filled in the piece they were missing. Today, the maximum mass that neutron degeneracy pressure plus the nuclear equation of state can support is what we call the Tolman-Oppenheimer-Volkoff limit, or the TOV limit, named for all three: Richard Tolman, J. Robert Oppenheimer, George Volkoff. Modern estimates, informed by decades of nuclear physics experiments and constrained by actual observations of massive neutron stars, place the TOV limit somewhere around 2.2 to 2.3 solar masses. A bit more precisely, constraints from a gravitational wave event in 2017, which we'll come to in a moment, have pushed some estimates toward about 2.17 solar masses as an upper bound, though the exact number still carries some theoretical uncertainty depending on what assumptions you make about the equation of state at the highest densities. But the rough answer is, somewhere near 2.2 solar masses, there is a wall. Below that wall, the nuclear equation of state, the stiffness of dense matter, the repulsion of the strong force can hold the star up. Above it, nothing can. Not neutron degeneracy pressure. Not the strong nuclear force. Not any combination of known physics. The gravity wins, the star collapses, and when it does, it becomes a black hole. This is not a calculation that physicists made up as a limit in the abstract. It is a limit that nature enforces. And we know nature enforces it because of what happened on the 17th of August, 2017. On that day, two detector networks, LIGO, the Laser Interferometer Gravitational Wave Observatory, with its twin detectors in Livingston, Louisiana, and Hanford, Washington, and Virgo, its European partner, in Cassina, Italy, detected a gravitational wave signal, not from the merger of two black holes as had been detected in earlier events. This was different. This was GW170817. The gravitational waves of two neutron stars spiraling together. For about 100 seconds, LIGO and Virgo recorded the characteristic chirp, the rising frequency of the waves as the two stars spiraled faster and faster, losing energy to the gravitational radiation, drawing together at a rate that made the signal sweep upward in frequency like a whistle climbing in pitch. And then 1.7 seconds after the merger signal, space telescopes detected a short gamma-ray burst. Then, over the following days and weeks, observatories around the world watched the afterglow, a kilonova, a burst of light from the debris carrying the unmistakable spectral signatures of heavy elements being forged in the collision: gold, platinum, iodine, uranium. The merger of two neutron stars makes the heaviest elements in the periodic table, scattered into space in the explosion. But for our purposes here, the question of the TOV limit, the wall above which a neutron star cannot exist. What mattered was the following. After the merger, what happened to the remnant? The total mass of the two infalling neutron stars was estimated at around 2.7 solar masses. That is well above the TOV limit, which means the merged remnant could not survive as a neutron star. It had to collapse into a black hole. The question was only immediately or after a brief delay. The gravitational wave signal cut off at the moment of merger, and no long-duration post-merger signal was detected, which means the remnant probably collapsed to a black hole quite quickly, within milliseconds. And this sequence, the merger, the kilonova, the rapid collapse, placed a constraint on the TOV limit. The remnant was too massive to survive as a neutron star. The ceiling had to be somewhere below 2.7 solar masses. Combined with the observation that 2.08 solar mass neutron stars exist and are stable, the ceiling was bracketed from above and below, somewhere between about 2.17 and 2.3 solar masses, depending on whose analysis you use. Benjamin Margalit and Brian Metzger published one of the key constraint papers in 2017. Luciano Rezzolla and colleagues published another in 2018. The TOV limit went from a theoretical parameter to an observationally bounded number. Physics at the edge of its known territory, triangulated by a collision 130 million light-years away. So when we say the TOV limit is approximately 2.2 solar masses, that is not a physicist's guess. It is a measurement. Indirect? Yes. Uncertain? Yes. But measurement nonetheless, a consequence of watching two dead stars spiral together for 100 seconds and then vanish. And now here is what makes that limit so astonishing to sit with. Imagine you are the matter at the center of a 2 solar mass neutron star. You are neutrons packed to nuclear density and beyond, carrying the full weight of 2 suns pressing down on you. You are subject to neutron degeneracy pressure, the quantum mechanical insistence that no 2 neutrons can share a state. You are subject to the repulsive core of the strong nuclear force, which is pushing back against your compression with a stiffness that no terrestrial material can approach. You are, in a sense, the final defense, the last thing between stability and total gravitational collapse, and you are holding. The star with 2.08 solar masses is holding. PSR J0740+6620 is spinning away in Camelopardalis, 12-ish kilometers across, stable. The pressure is winning, but add a tiny bit more mass. Push over approximately 2.2 solar masses, and then nothing holds. Not degeneracy pressure, not the strong force. The gravity is greater than the sum of everything quantum mechanics and nuclear physics can muster. And the star falls all the way down, through a neutron star, through whatever hypothetical exotic matter might exist at its core, through every transition and phase boundary we've discussed, and past them all into a black hole. There is no stable object between a maximum mass neutron star and a black hole, no intermediate step, no almost a black hole. The transition is, in some sense, instantaneous. One side of the limit, a neutron star, exotic and extreme, but stable, measurable, with a radius and a surface and a magnetic field. The other side, a black hole, an event horizon, a region of space from which nothing returns. The TOV limit is the sharpest edge in stellar astrophysics. And here is the thing about PSR J0740+6620, our 2.08 solar mass champion. It exists about 1/10 of a solar mass, maybe a bit more, below the TOV wall. That's the margin, that's how close to the edge of existence a neutron star can get and still be a neutron star. And its radius is still 12-ish kilometers. The extra mass isn't making it bigger, it's making it denser. It's pushing the central density higher, compressing the inner core further, and yet the outer radius barely moves. This is the paradox the nicer data hammered home. Mass and radius are decoupled in this regime. They are not simply proportional. And the reason they are decoupled is that the relationship between pressure and density in ultra-dense matter, what physicists call the equation of state, is not a simple linear function. At different density regimes, matter stiffens or softens in ways that change how much adding more mass compresses the star. The radius is mostly set by the matter at intermediate densities, the outer core. The central density can change substantially with mass without dramatically changing the overall size. You can think of it this way. Imagine you have a ball of memory foam, the kind that slowly springs back when you press it. If you push down gently, it compresses a lot. But once it's compressed past a certain point, it gets firmer and resists further compression. So adding more pressure beyond that point doesn't compress it much more, it just makes the interior denser and the exterior spring back to roughly the same size. That's not a perfect analogy. See, neutron star matter is incomparably more complex than memory foam. But the qualitative behavior is similar. The outer layers are relatively compressible, the inner core is stiff, and the result is that the radius is roughly constant across a wide range of masses, while the central density varies enormously. This is actually one of the most important things the nicer measurements gave us. Not just a number, 12 kilometers, but a constraint on the equation of state itself. Because if you know the mass and radius of multiple neutron stars, you can work backward and ask, what relationship between pressure and density produces those combinations? What kind of matter at those densities has those properties? Two stars with very different masses but similar radii tell you something specific about how stiff the matter is at intermediate densities. They place the neutron star equation of state inside a box. They rule out equations of state that are too soft, where the matter would compress too easily and the radius would shrink significantly with added mass, and rule out equations of state that are too stiff, where the matter would resist compression so strongly that you couldn't get something as compact as 12 kilometers at any mass. The surviving equations of state are those that thread through all three nicer measurements, PSR J0030, PSR J0740, and PSR J0437+4715's 11.36 kilometers. And here is where the door opens to the core, because different equations of state don't just predict different mass-radius relationships, they predict different compositions. What the matter actually is in the deepest interior depends on how stiff the equation of state is and how that stiffness relates to the density. So measuring the radius, timing X-ray photons to 100 nanoseconds on the International Space Station, watching the gravitational light bending distort the pulse profiles of spinning pulsars, is also, indirectly, measuring the question of what the core is made of. We have not answered that question yet, but we have narrowed the space of possible answers. The nicer data, combined with GW170817, combined with the radio timing measurements of PSR J0740's mass, together rule out a large fraction of the theoretical landscape. Some equations of state are simply dead, gone, inconsistent with observation. The space that remains is still broad enough to encompass several very different possibilities, but it is narrower than it was before 2017, and narrower again than it was before 2019, and narrower still after the 2021 and 2024 measurements. Each year, the unknown shrinks slightly, but it is still unknown. So, let's go back down into the star, past the nuclear pasta, past the inner crust, through the crust-core boundary, where the discrete nuclear lattice dissolves into a continuous neutron fluid. Into the outer core. This is the largest single layer of the star. It spans perhaps 8 kilometers of radius, from just inside the crust down to wherever the inner core begins. A boundary that is not sharp the way the neutron drip line is sharp, but rather a transition that happens gradually as the density climbs past roughly twice nuclear saturation density. The outer core is, in terms of volume, most of what a neutron star is. And it is strange. The neutrons here, the vast majority of the matter, perhaps 90% of the particles by number, with the remainder being protons, electrons, and a smattering of heavier leptons called muons, are not flowing the way water flows. They are not a hot, agitated gas. They are cold by stellar standards and quantum mechanical in a deep way. The neutrons in the outer core are believed to form a superfluid. Superfluidity is one of the most striking phenomena in quantum mechanics. It occurs when particles, fermions like neutrons, under the right conditions, pair up and behave collectively as a single quantum state. The Cooper pairing mechanism, familiar from superconductivity in metals, has an analog in nuclear matter. Paired neutrons in a neutron star's outer core can form what physicists call a neutron superfluid, matter that flows without any friction, without any viscosity, without any resistance. Not because it's slippery in an ordinary mechanical sense, but because the quantum state it occupies cannot dissipate energy in the way ordinary matter does. As superfluid flows around obstacles without slowing, it climbs up the walls of containers. It moves in ways that seem to violate intuition because it is genuinely not obeying the same rules as everyday fluids. And this behavior at neutron star densities and in a star 12 kilometers across has consequences. Similarly, the protons in the outer core, a small minority, perhaps 5% or so of the particles, are believed to form a superconductor. An ordinary electrical conductor like copper wire has some resistance. Electrons bump into impurities and lattice vibrations and lose energy. A superconductor has zero resistance. Current flows indefinitely without loss, and in the protons of a neutron star's outer core, the pairing mechanism produces a proton superconductor, meaning the star's interior carries electric currents with perfect efficiency and maintains magnetic fields in a very specific, quantized way. The combination, a superfluid of neutrons and a superconductor of protons, is one of the most exotic thermodynamic states we know of in the universe, and we have evidence for it. In 2010 and 2011, astronomers studying Cassiopeia A, a young supernova remnant, the remains of a star that exploded roughly 340 years ago, observed from Earth since around 1680, detected something puzzling in the X-ray data from the neutron star at its center. The neutron star was cooling faster than expected, significantly faster. Its surface temperature was dropping at a rate that simple models of neutron star cooling could not explain. Two independent teams, one led by Danny Page, another led by Peter Sternin, proposed the same explanation almost simultaneously in 2011. The rapid cooling, they argued, was caused by the onset of neutron superfluidity in the core. As the neutrons pair up and form the superfluid, they release a burst of neutrino emission, an efficient cooling mechanism that temporarily accelerates the temperature drop. The Cassiopeia. A neutron star was young enough and cool enough that astronomers were watching it cross this transition in real time. Watching a neutron star's superfluid switch on. Through X-ray photons counted by space telescopes, if correct, and the explanation has held up to subsequent analysis, though some uncertainty remains in the exact parameters. It means we have observational evidence for the superfluid interior of a neutron star. Not a theoretical prediction, an observed consequence. A star cooling too fast in a way that only makes sense if its interior is undergoing a quantum phase transition. The universe continues to exceed expectations. And there is one more piece of this outer core picture that we can observe directly. More directly, in fact, than the Cassiopeia A cooling, because it happens in real time, repeatedly, in dozens of pulsars we have timed for years or decades. When a pulsar forms, it is spinning rapidly, sometimes hundreds of times per second, and over time it slows down. The magnetic field sweeping through space carries away rotational energy, and the pulsar gradually spins more and more slowly. This spin down is extremely regular, extremely predictable. Pulsars are, in some ways, the most precise natural clocks in the universe. Astronomers who time them carefully can predict their rotation to extraordinary precision, months or years in advance. Except occasionally a pulsar cheats. It suddenly spins up, not by much, although the fractional change in rotation rate is tiny, on the order of parts in a million to parts in a billion, but it is sudden, happening on timescales of hours to perhaps days, essentially instantaneous compared to the pulsar's slow, gradual spin down over years. And then the pulsar slowly returns to its previous spin down trend, over weeks to months, as if settling back into its groove. These events are called pulsar glitches. And the Vela pulsar, a well-studied pulsar in the constellation Vela, about 1,000 light-years away, spinning roughly 11 times per second, is the most famous glitcher. It glitches every few years. And it's not alone. Dozens of pulsars have now shown glitching behavior. The explanation, worked out over decades of theoretical development, involves the superfluid interior and the rigid crust, and it goes something like this. The superfluid neutrons in the outer core carry angular momentum in a specific quantum mechanical way. A rotating superfluid doesn't rotate uniformly like a solid body. Instead, its rotation is carried by quantized vortices, tiny whirlpools threaded through the superfluid, each carrying a precise quantum of angular momentum. As the star spins down, these vortices need to move outward to accommodate the decreasing rotation rate, but the vortices can pin to defects in the nuclear pasta layer of the crust. They get stuck, and as the crust slows down, spun down by the magnetic field's drag, the superfluid interior, whose vortices are pinned, doesn't slow at the same rate. A lag builds up between the spinning crust and the spinning superfluid. Angular momentum accumulates in the superfluid, and then suddenly the vortices unpin, triggered perhaps by the crust cracking under the accumulated stress, a star quake, or by some other instability. When they unpin, the superfluid's pent-up angular momentum transfers rapidly to the crust. The crust spins up. The pulsar glitches. We see it as a sudden fractional jump in the rotation rate and then a slow relaxation as the coupling between superfluid and crust re-equilibrates. The Vela pulsar's glitches are our window into the rotating superfluid interior of a neutron star. Every time it lurches, every sudden fractional spin-up that our radio telescopes catch, it is the sound of a quantum ocean sloshing. So we have watched the Vela pulsar lurch, we have felt the quantum ocean slosh, and now, slowly, gently, if you're still with me, let's keep falling inward, because we haven't reached the center yet. We've come down through the outer crust, that rigid crystalline lattice of neutron-rich nuclei suspended in a sea of degenerate electrons. We pass through neutron drip, that threshold around 4 × 10 to the 11th grams per cubic centimeter, where nuclei grew so saturated, so overstuffed with neutrons that they simply couldn't hold them anymore, and the neutrons leaked out, not evaporating, not escaping in the usual sense, but dripping quietly and inevitably into a free ocean that coexists with the crust. We moved through nuclear pasta, those extraordinary shapes that competition between the strong nuclear force and electrostatic repulsion sculpts out of matter at the crust-core boundary, gnocchi, spaghetti, lasagna, antipasta. Material that Kaplan and Horowitz calculated to be roughly 10 billion times stronger than steel, the strongest substance anywhere in the known universe, shaped like something you'd find in a nice Italian restaurant. And we've arrived in the outer core. Here, the density climbs past nuclear saturation density, past that benchmark of roughly 2.3 times 10 to the 14th grams per cubic centimeter, the density of an atomic nucleus. And the matter has transformed into something that has no equivalent anywhere in ordinary experience. There are no atoms here, no atomic nuclei in the usual sense. The pressure is so immense that protons and electrons merged long ago to form neutrons, and those neutrons now exist in an unbound, free state. A sea of them, hundreds of millions of them packed into each cubic centimeter, closer together than the protons and neutrons inside any atom you've ever touched. And here, and this is one of the genuinely astonishing things that modern physics has figured out about these places, here, those neutrons are not simply a very dense, very hot gas. They are a superfluid. We talked about this in relation to the glitches, to the vortices and the pinning and the sudden spin-up of the Vela pulsar. But let's sit with what that actually means for a moment, because it is remarkable. A superfluid is a state of matter in which the fluid flows with absolutely zero viscosity, no friction, no resistance. If you stirred a superfluid in a perfectly sealed container, it would keep circulating forever. Not approximately forever, not for a very long time, but indefinitely, with no energy loss whatsoever. On Earth, superfluidity is an exotic laboratory phenomenon that occurs in helium cooled to within a degree or two of absolute zero. It requires extraordinary conditions. It is fragile and strange and wonderful. Inside a neutron star, superfluidity occurs in an environment of crushing pressure and temperatures that, even though they've cooled considerably from the star's birth, still reach around 1,000,000 degrees Kelvin or more. The neutrons are superfluid not because they are cold in any intuitive sense, but because the quantum mechanical conditions of their density and pairing are right. Quantum mechanics at planetary scale expressed in a body that fits inside a city. And there is more. The protons in the outer core, a minority of the particles there, roughly 10% or so alongside the dominant neutron fluid, those protons are believed to form a superconductor, not a material that conducts electricity very well. A true superconductor in which electrical current flows with zero resistance, and in which magnetic fields are carried in quantized flux tubes rather than spreading smoothly through the material. So picture what the outer core of a neutron star actually is. Not a liquid, not a solid, not a plasma in the conventional sense. A quantum fluid, mostly superfluid neutrons flowing without friction, threaded by quantized vortices that carry its rotation, coexisting with superconducting protons that carry magnetic flux in bundles, all of it at densities so high that an entire solar mass of this material fits inside a sphere roughly 10 or 11 kilometers across. A quantum ocean contained inside a ball you could drive across in about the time it takes to make a cup of tea. This is not a hypothetical. This is not a calculation on a whiteboard that physicists believe probably applies to something far away. There is evidence, real, measured evidence. In 2010 and 2011, something unexpected happened in the data being collected from Cassiopeia A, a young neutron star only about 330 years old, the remnant of a supernova that was probably observed on Earth in around 1680, located about 11,000 light-years away. Astronomers had been monitoring Cassiopeia A with the Chandra X-ray Observatory for about 10 years, and they found that the neutron star was cooling faster than models predicted, not dramatically faster, measurably, carefully, precisely faster. The research teams led by Danny Page and by Peter Sternin, publishing in 2011, argued that this rapid cooling could be explained if the neutron star had recently, within the last century or so, undergone a phase transition in its interior. The protons in the core had just crossed the temperature threshold to become a superconductor. When a material becomes superconducting, it releases a burst of neutrinos in a process called the Cooper pair, breaking and formation process. And those neutrinos carry energy away, carrying heat out of the core on timescales that Chandra could actually detect as a cooling anomaly. In other words, we might have caught a neutron star's interior changing state in real time over the span of a human observing campaign. Cassiopeia. A isn't proof beyond all doubt that the interior is a superfluid superconductor. Science doesn't work quite like that, but it is exactly the kind of signal you'd expect to see if it is. And it is one of the most direct observational links we have between the theory of the neutron star's quantum interior and a measured astronomical phenomenon. The Chandra data and the Page and Sternin analyses gave the superfluid superconducting core model some of its firmest empirical roots. And that's the outer core, dense, quantum, strange in ways that make superfluidity feel almost comfortable. Now we go deeper, past the outer core at densities climbing above roughly twice nuclear saturation density. We enter the inner core, and here something changes. Not in the star. We don't know what changes in the star precisely, and that's the point. What changes is the conversation, because right here, at the deepest interior of a neutron star, we reach the edge of what human knowledge can currently tell you. We reach a genuine frontier, not a gap in the popular understanding, not something the textbooks have explained but science communicators haven't gotten around to yet. A frontier in the technical literature, in the papers coming out of physics departments and astrophysics groups today, in the equations that people are still fighting about. Nobody knows what matter is at the very center of a neutron star. Say that again slowly. Nobody knows. Now that doesn't mean we have no ideas. We have several, and they're fascinating, and each of them says something profound about the fundamental nature of matter. Let me walk you through them gently, one at a time. The first candidate is hyperons. A proton and a neutron are both baryons, particles made of three quarks, the fundamental building blocks of nuclear matter. Specifically, a proton is made of two up quarks and one down quark, and a neutron is two down quarks and one up quark. That's what most of the matter in the outer core is, just neutrons and protons, combinations of up quarks and down quarks. But there's a third type of quark, the strange quark. And at the densities in the inner core, it may become energetically favorable for some of the neutrons to convert to particles that include a strange quark. Particles called hyperons, lambda particles, sigma particles. These exist briefly in particle accelerators here on Earth, created in high-energy collisions and decaying in fractions of a second. In a neutron star's inner core, the pressure might be so extreme that they become stable, a permanent, exotic ingredient in the deepest soup. The problem, and this is one of the most vexing unsolved problems in the field, known as the hyperon puzzle, is that if you add hyperons to your model of a neutron star's inner core, the matter becomes softer, more compressible. And a softer equation of state means the star cannot support as much mass before collapsing. If you include hyperons in your models, the maximum mass you get for a neutron star at the top of the TOV limit drops below 2 solar masses. But we have measured neutron stars above 2 solar masses. PSR J0740+6620 sits at about 2.08 solar masses. That star exists, it is there. It is not a black hole. So either hyperons are present and something else is stiffening the matter in a way our models don't yet capture, or hyperons are suppressed by some mechanism we haven't worked out, or the equation of state is doing something more complicated than our current theories describe. The hyperon puzzle is the kind of thing that keeps nuclear physicists and astrophysicists writing papers and attending conferences and disagreeing politely and sometimes less politely over coffee. It is an open wound in the theory of dense matter. And it matters because the answer changes what the core is made of. The second candidate is a Bose-Einstein condensate of mesons. At high enough densities, theorists predict it might become possible for pions, particles made of a quark and an antiquark, or kaons, which include a strange quark, to condense into a new quantum state. A Bose-Einstein condensate, a collective quantum ground state where many particles all occupy the same quantum configuration simultaneously. The condensate, like the superfluid, is a macroscopic quantum phenomenon. It behaves in ways that ordinary matter simply doesn't. Kaon condensation in particular has been studied fairly extensively. The signature of a kaon condensate would again soften the equation of state, similar tension with the hyperon puzzle, and detecting it from the outside is extremely difficult. It would show up, most likely, as a signature in how the maximum mass and radius of neutron stars depend on each other. The very measurements NICER is making, the curves that theorists are trying to fit. And the third candidate, perhaps the most radical, is free quarks. At low enough energies and high enough temperatures, in the early universe, for instance, or briefly in heavy ion collisions at CERN's Large Hadron Collider, quarks can exist freely, unconfined, not bundled into protons and neutrons. This state is called quark-gluon plasma, or deconfined quark matter. The question is whether, at the extreme densities of a neutron star's inner core, something similar might occur, whether the neutrons themselves might dissolve, their quarks no longer confined individually to each nucleon, but instead free to roam through a larger volume of strange quark matter. This hypothetical state comes in several theoretical flavors. There is simply deconfined quark matter, a sea of free quarks. There is strange quark matter, which includes strange quarks as a stable component alongside up and down quarks, and which some theorists have proposed might actually be the true ground state of matter under certain conditions, more stable under those extreme conditions than ordinary nuclear matter. And then there is color superconducting quark matter, in which the quarks themselves pair up analogously to the way electrons pair in a conventional superconductor, forming a new kind of quantum condensate with properties unlike anything else in physics. Color superconductivity, held inside a star you could fit inside a city, made of particles smaller than anything you can image, in a state that has no name in everyday language. Here's the honest summary. We don't know which of these is right. We might not have just one of them. The core might transition through several phases as you fall inward, a kind of nested set of exotic states, each one deeper and stranger than the last. Or none of the candidates might be exactly right, and the true state of matter at those densities might be something the models haven't fully captured yet. What NICER is doing, measuring real stars, finding that a 2 solar mass star and a 1.4 solar mass star are both about 12 kilometers across, is data that constrains these models. Not enough data yet to decide between them definitively, but data that is cutting away the parameter space, narrowing the field, telling the equations what they have to be compatible with. Each measurement is a boundary condition imposed on the theory. Each precise radius is a fence that the equation of state has to stay inside, and the inner core, at the very center, is where the fences are still far enough apart that several very different rooms can still fit between them. That is the frontier. Let's step back now. Come back up through the layers slowly. Back through the superfluid outer core with its quantum vortices and its superconducting protons. Back through nuclear pasta, lasagna, spaghetti, gnocchi, and neutron drip, and the crystalline outer crust back toward the surface, because there's something we should pause on before we zoom all the way out. Something that lives at the intersection of the rigid crust and the extraordinary magnetic fields that some neutron stars carry. Something that sits at the most violent end of the neutron star spectrum, and that on one specific day in December of 2004 reached across 50,000 light-years of empty space and disturbed our own planet. Magnetars. Most neutron stars have magnetic fields that are already extraordinary, around 10 to the 12 or 10 to the 13 Gauss, a trillion or so times stronger than Earth's magnetic field. The physics of why they're so strong is related to the conservation of magnetic flux during the stellar collapse. The progenitor star had a magnetic field spread across a volume millions of kilometers across, and when that volume compressed to a 12-kilometer sphere, the field lines were squeezed together and concentrated by a factor of billions. But magnetars are something else. Their fields reach up to around 10 to the 15th Gauss, a quadrillion times stronger than Earth's, 1,000 times stronger than an ordinary pulsar. Fields so intense that the quantum vacuum itself is distorted. The empty space around the star is changed by the magnetic field in ways that have real physical consequences. Atoms near a magnetar's surface would be squeezed into elongated needles along the field lines. If you could somehow move a credit card to within about halfway to the moon's distance from a magnetar, still hundreds of thousands of kilometers away, the field would be strong enough to erase it entirely, pulling the magnetic domains apart. You are not going anywhere near a magnetar. Magnetar fields are thought to arise through a dynamo process during the star's very first seconds of life, when it is born spinning extremely fast, and the interior is still hot enough and fluid enough for convective motions to amplify the magnetic field through large-scale circulation. Not all neutron stars go through the right conditions for this, which is why magnetars are relatively rare. And the reason magnetars are particularly relevant to our story about the interior is that their extraordinary magnetic fields put the crust under extraordinary stress. The magnetic field is not static, it evolves and twists over time, driven by currents in the crust and the core. As it changes, it exerts forces on the rigid crust. The crust resists. Stress builds. And sometimes the crust gives way. A magnetar starquake is not like a geological earthquake. The energies involved are incomprehensible by comparison. And on the 27th of December 2004, one of them happened, or rather, the radiation from one of them arrived at Earth on that day, having left its source about 50,000 light-years away. The magnetar is called SGR 180620. SGR stands for soft gamma repeater, a class of sources that emit repeated bursts of gamma rays and X-rays. SGR 180620 sits in our own galaxy, toward the galactic center, at a distance of roughly 50,000 light-years. On that December day, it produced what astronomers call a giant flare, a catastrophic rearrangement of its magnetic field and crust, an energy release in about 0.2 of a second that was genuinely staggering. The flare outshone, in gamma rays, the full moon in visible light. That sentence needs a moment to settle. From 50,000 light-years away, that's roughly 500 quadrillion kilometers, a brief, violent rearrangement of a city-sized star's crust produced a flash brighter than our moon. It was the brightest extrasolar event ever recorded reaching Earth. Gamma-ray detectors on multiple spacecraft were saturated. Their instruments simply couldn't record the full brightness because the signal was too strong. Scientists from the event included David Palmer and colleagues who published the detailed account in Nature in 2005. The flare didn't just light up instruments in space, it disturbed the ionosphere, the upper atmosphere of Earth. The gamma-ray pulse ionize the night-side atmosphere at the altitude range typically only affected by solar X-rays or large solar flares. We can measure the ionosphere's state quite precisely because it affects radio wave propagation, and on that day, the signal from 50,000 light-years away left a detectable fingerprint in our own planet's atmospheric layer. Think about that. You were probably alive on the 27th of December 2004. The planet you were standing on was measurably, physically altered, however briefly and however subtly, by the starquake of a city-sized magnetic object 50,000 light-years away. SGR 180620's flare was a direct consequence of crust physics. The crust fractured. The magnetic field configuration jumped to a lower energy state. The energy released in that transition rippled outward. It's the same physics, the same rigid crust, the same accumulated magnetic stress, the same sudden yield that produces the smaller, more ordinary bursts that soft gamma repeaters produce more regularly. The giant flare of 2004 was just the largest, most dramatic expression of it, and all of it points back to the interior, to the structure of the crust, to the nuclear pasta, and the density gradients and the geometry of the magnetic field threading through a body the size of a city. The universe did not give us gentle access to neutron star interiors. It gave us flashes and pulses and glitches and, very occasionally, signals of extraordinary violence that carry interior information across 50,000 light-years of night. And then it gave us NICER, which is, in some ways, the calmer, more methodical version of the same conversation. Instead of waiting for a catastrophic event and reverse engineering what it tells us, NICER sits on the International Space Station, on the exterior, mounted where it can see the sky, and watches carefully, patiently, for the periodic X-ray pulses of millisecond pulsars, timing each photon to within 100 nanoseconds, building up a picture of the pulse profile over weeks and months of observation, feeding that profile into the models that fold in general relativistic light, bending to extract the star's mass and radius simultaneously. It is, in its own way, as astonishing as the 2004 flare. Just quiet. Just precise. Just a machine on a space station counting light one photon at a time to tell us what the inside of a star is made of. And now let's zoom out completely. Let's come all the way back. Not just to the surface, not just to the outer crust, all the way out. To the perspective that takes in the whole thing. A neutron star is a city made of the core of a dead sun, packed tighter than anything else that still has a surface, tighter than anything that hasn't yet surrendered to becoming a black hole. At its surface, 12 kilometers or so from the center, gravity is 200 billion times stronger than what holds you in your chair. Something the size and weight of a marshmallow falling onto that surface would arrive with the energy of an atomic bomb. The escape velocity is somewhere between 1/3 and 1/2 the speed of light, depending on the star's mass. Light itself bends visibly around it, not just theoretically, but measurably, detectably, in the way that the X-ray brightness curves that NICER measures are distorted by the warping of space-time, allowing us to peek around the edges of the star and glimpse hot spots that would otherwise be hidden on the far side. It is, by almost any reasonable definition, one of the strangest things in the universe, and yet it is made of matter. Real matter, subject to real physical laws. The same quarks that make up the proton in a hydrogen atom in your body are the quarks that make up the neutrons in the outer core of a neutron star. The same electromagnetic force that holds atoms together, the same strong nuclear force that holds nuclei together, the same quantum statistics that prevent two electrons from occupying the same state in your atoms. All of these operate inside a neutron star. The laws don't change, only the conditions do. And what changes the conditions is compression, pure, relentless gravitational compression, bringing matter closer and closer together than it was ever arranged in any star that survived. The layers inside a neutron star are, in a sense, a map of what matter does when you squeeze it past every threshold. First a crystal, then a dripping neutron ocean, then exotic pasta shapes, then a frictionless quantum fluid, and then, at the very center, a question that physics hasn't answered yet. That question is not a failure, it is a frontier. Science proceeds by mapping what is known until the boundary between the known and the unknown becomes clear enough to work at. And the decades of work that went into understanding neutron stars, from Walter Baade and Fritz Zwicky writing down the prediction in 1934, 2 years after James Chadwick discovered the neutron itself, through Jocelyn Bell Burnell sitting at her radio telescope in 1967 and noticing a signal repeating with such clockwork precision that she and her colleagues nicknamed it LGM-1 Little Green Men, through decades of pulsar timing and the cataloguing of glitches and the hard theoretical work on nuclear pasta and superfluid dynamics through the gravitational wave detection of GW170817 in 2017 and the way that merger events sharpened the Tolman-Oppenheimer-Volkoff limit, all of that work has brought the boundary between known and unknown to a very specific location. The boundary is the inner core. Everything outside it we understand reasonably well, or at least we have frameworks for it that we believe in and that make testable predictions. The boundary is in the right place, not vague, not everywhere, not a general admission of ignorance, but a precise layer of matter at a precise density range where our best theories diverge and the measurements have not yet chosen between them. That is remarkable progress. That is the Oppenheimer-Volkoff calculation of 1939 being improved not by 3%, not by 30%, but by a factor of 3, because the 1939 calculation forgot the strong nuclear force. That is NICER measuring a real star in 2019 and finding that it has lopsided crescent-shaped hotspots in one hemisphere rather than the neat antipodal dipole that every textbook diagram shows, finding that the magnetic field, even on the surface, is more complicated and more beautiful than the simple bar magnet anyone drew. That is science doing what science actually does, which is not confirming what we thought we knew, but being surprised. The hotspots of PSR J0030+0451 are not where they were supposed to be. The 2021 reanalysis hinted that there might even be a third one. The magnetic field of a neutron star is not a bar magnet. It is something more complex, something that NICER is helping us map for the first time with real measurements rather than theoretical assumption. And PSR J0740+6620, the heaviest, precisely measured neutron star at about 2.08 solar masses, has essentially the same radius as PSR J03+0451 at about 1.4 solar masses. Add 50% more mass to a neutron star, and it doesn't get bigger, it just gets denser. The matter finds some way, some combination of quantum pressure and possibly exotic physics, to resist collapse without expanding. The star doesn't puff up. It holds the line at about 12 kilometers while the density at its center climbs. It holds the line until it can't. At around 2.2 to 2.3 solar masses, the modern observational and theoretical estimate of the TOV limit, tightened considerably by the neutron star merger of GW170817 and by the NICER mass radius measurements, something gives. The neutron star collapses, not slowly, not gradually, catastrophically. It becomes a black hole. The threshold is not a metaphor or a round number. It is a real physical boundary, as real as the melting point of ice or the boiling point of water, derived from the same physics. And the physics says there is a precise weight that no neutron star can survive, no matter what its interior is made of, no matter how exotic the matter at its core. The TOV limit is, in a sense, the final word on the neutron star's story. Everything inside it, the quantum ocean, the pasta, the exotic core candidates, everything is in the business of holding up against gravity, of keeping the star from collapsing, of negotiating between pressure and compression for as long as possible. And the TOV limit is where the negotiation ends. It is, quietly, one of the most profound things about neutron stars. They are an argument, a sustained physical argument between the forces of nature about whether this much matter can stay this way. The result of that argument, measured in solar masses to 2 decimal places, is the TOV limit, and the measured existence of PSR J0740+6620 at 2.08 solar masses tells us the argument can go nearly that far. And GW130817 and the analyses by Margalit and Metzger in 2017 and Rizzola and colleagues in 2018 tell us it can't go much further. The argument is nearly resolved at 2.2 suns. After that, there is only collapse. And somewhere tonight, in the tens of thousands of neutron stars in our galaxy, the argument is going on. Starquakes are fracturing crusts. Pulsar glitches are carrying quantum angular momentum from the superfluid to the rigid shell. Magnetar fields are twisting and building and occasionally releasing vast amounts of energy in gamma-ray flares. A handful of millisecond pulsars are spinning hundreds of times per second, their equators moving at significant fractions of the speed of light, the roundest objects in the universe, smoother than any sphere we could machine on Earth, their mountains no taller than a centimeter or two, and PSR J0740+0451 AD, the fastest known rotating neutron star, is spinning at 716 times per second. Its equator is moving at roughly 24% of the speed of light, 70,000 kilometers per second. In the time it takes you to read this sentence, that star completes somewhere around 2,000 full rotations. We know all of this, not in the way we know myths or averages or approximations. We know it in the way science knows things, which is, we measured it, we checked the measurement, and we understand why the measurement means what it means. The universe built these objects from the same material that everything else is built from, and then arranged that material in a way that gives us access to physics we cannot replicate in any laboratory on Earth. They are, in a very real sense, experiments. Extreme state experiments that nature ran on a scale and under conditions we can observe but not create. And for the better part of a century, we theorized about them from a distance. NICE had changed something in that relationship. It moved us from theorizing at a distance to measuring with precision, timing photons to 100 nanoseconds, building pulse profiles, letting general relativity itself, the bending of light by the star's own gravity, serve as the measuring tool, finding that the star is 12 kilometers across, finding that the hot spots are not where the textbook said, finding that more mass doesn't mean more size, just more density, until the limit. These are not incremental improvements to a settled picture. They are the beginning of a new kind of conversation between us and these objects, a conversation where we ask real questions with real instruments and get real numbers back, and then argue about what those numbers mean for what is happening at the deepest, densest, most unknown place in the observable universe. The center of a neutron star, a place that might hold hyperons, strange quark-bearing particles that only live for fractions of a second in our accelerators, but may be permanently stable there, under those pressures. A place that might hold a Bose-Einstein condensate of kaons or pions, quantum matter in its strangest collective form. A place that might hold free quarks, unconfined from the nucleons that contain them everywhere else we have ever looked, possibly in a color superconducting phase that would require new physics to fully describe. A place where we simply do not yet know, and we will find out. Not all at once, not with a single measurement. But the curve of neutron star science has been consistently and unmistakably toward more knowledge, not less. From prediction in 1934 to detection in 1967, from timing pulsars in radio waves to timing them in X-rays to 100 nanoseconds from a detector on the space station. From a TOV limit calculated wrong by a factor of 3 in 1939 to 1 measured by gravitational wave astronomy in 2017. From textbook dipole hotspots to measured crescent-shaped lopsided magnetic configurations. From vague, we don't know the interior, to a precisely located frontier at a precisely specified density range with precisely specified theoretical candidates. The blank is getting smaller, and what fills it will likely be one of the most significant discoveries in fundamental physics, because whatever is happening at the center of a neutron star is matter behaving in a way that matter has never been observed to behave. It is either familiar particles in unfamiliar arrangements, or genuinely new phases of matter that expand what we mean by the word matter itself. Either answer would be extraordinary. And here is the thing that I want to leave you with as you settle in wherever you are. Wherever that is. A bed, a couch, a train moving through the dark, a room with a lamp still on somewhere. The matter you are made of and the matter at the center of a neutron star are, at the deepest level, the same matter. The quarks in the protons and neutrons of your atoms are the same quarks that were forged in the first seconds of the universe, that later fused in the cores of stars, that scattered across space when those stars died, that gathered into planets and eventually into the atoms of your body. Some of those stars, the most massive ones, 8 to 20 times the mass of the Sun or more, did not simply fade, they collapsed, and the collapse created neutron stars. The matter that didn't make it into the collapsed remnant scattered outward in the supernova, out into the interstellar medium, and across billions of years and enormous distances found its way, eventually, into the molecular cloud that became the solar nebula that became the Sun and the Earth and you. You and the neutron star are made of the same material. You are the low-density version, the easy arrangement, the arrangement that permits atoms and molecules and chemistry and biology, and the improbable structure of consciousness, reading words at 3 in the morning. The neutron star is what that same material looks like when gravity has done its most extreme work on it, when it has been compressed past every threshold, past the point of atoms, past the point of nuclei, into something that has no name in everyday language. The comparison is not a metaphor. It is a fact. The quarks are real quarks. The same quarks, arranged differently. At the start of this journey, we mentioned the famous line, the sugar cube, the billion tons, the cliché that every video about neutron stars opens with and then stops at, as if that were the whole story. And we said that line was the least interesting thing, that it was only half true depending on which layer you sampled, that the density climbs by millions of times as you fall from the atmosphere to the core, and that the famous number belongs only to the deepest part, the part we are still trying to understand. And that, I think, is the most honest summary of where we are. The famous line is true, roughly. But the other truth is layered, a centimeter-thick plasma atmosphere where the X-rays form, a crystalline crust of neutron-rich nuclei, a drip point where neutrons begin to leak free, nuclear pasta stronger than anything else in the universe, shaped by physics into forms with the names of food, a superfluid quantum ocean of neutrons rotating in quantized vortices evidenced by the glitches of the Vela pulsar and the cooling curve of Cassiopeia A, a hard ceiling at 2.2 solar masses where even all of that yields to gravity. And at the very center, an honest question that science has not yet answered, surrounded by beautiful, specific, named candidates that the next generation of instruments is working to test. NASA is not done. The measurements are still coming in. PSR J0430+4715, the nearest millisecond pulsar at about 510 light-years, gave us a radius of around 11.36 kilometers in 2024. Another data point, another fence post, another boundary condition that the equations have to live inside. The picture is filling in, slowly, carefully, one photon at a time. And if you're still awake, which is perfectly fine, I genuinely hope you found this interesting enough to make the trade worthwhile, then you know more about the inside of a neutron star than most people ever will. You know the layers have names. You know the pasta is real. You know the hot spots are not where they were supposed to be. You know the limit has a name, and the names of the three people it honors: Tolman, Oppenheimer, Volkov. You know the founding calculation was off by a factor of 3. You know what NICER is and where it lives and how it works, and you know that at the very center, the universe is keeping a secret that it has not yet shared. A secret that may be strange quarks or kaon condensates or color superconducting matter or something we haven't fully named yet. A secret that sits 12 kilometers from the surface of a star rotating hundreds of times per second, 1,000 light-years away, quietly making the universe slightly more interesting than it would otherwise be. That is a good thing to carry into sleep, I think. The universe is stranger at its most compressed than our everyday language has words for. And we, this small, improbable species on a pale blue dot, have put an instrument on the outside of a space station and pointed it at a pulsar 1,000 light-years away and read its X-ray pulses to within 100 billionths of a second, and from that we have measured the size of a star. We have done that. That happened. The numbers are in the literature. It is, quietly, one of the most extraordinary things our species has accomplished, and we are not done. If you enjoyed this slow journey through the layers of one of the universe's most extreme places, a gentle like or subscribe would mean a great deal. Small creators like me really do rely on your support to keep these going, and it helps more than you might think. And I'd love to know where you're listening from tonight, and what time it is in your corner of the world. Leave it in the comments when you wake up, or right now if you're still awake and wondering about quarks. Until next time, calm mind, clever dreams. I'll be here tomorrow night.